For the only talk of this afternoon session and the last talk of this week, it's my pleasure to introduce Oleksander Gamayun from Warsaw University, who will tell us about effective form factors for free fermionic models at finite temperature.
Right, okay, thank you. Good afternoon, everybody. It's my pleasure to give a talk this fantastic place, so thanks organizers. And today I'll present you research that I did with three groups of people, like guys in Kyiv, in Amsterdam, and now in Warsaw. All this work in progress. And it will be mostly about how to evaluate asymptotics of certain free form determinants at finite temperature. But before to jump into very technical part, let me start with small motivation, why we are interested in, and what are the challenges of computing integrable systems at finite temperature. So here there are like examples of two the most canonic integrable models, namely the Heisenberg spin chain and the linear gas. And the most important observables in both of these theories are mainly two-point correlation functions, so either it's spin-spin correlation function, density-density, or it could be field-field correlation functions so computed at some state. And exactly this object have the most direct relation to various experimental technique, so like neutron scattering, spectroscopy experiments, and interference experiments. So that's why it's very important not just to know the spectrum of the theory, but also be able to compute some information about correlation functions. So I will explain this next slide. So it's some state, and because it's in bold, it's many particle state. So indeed, let's start with, with what is Q. Yeah, so Q is typical state, and because of integrability, we just know well how to compute it. So in most simple cases, it's just a linear combination of plane waves with prescribed amplitudes, which we know from beta ansatz. In more sophisticated case, but it can be expressed as algebraic beta ansatz as action of B operators. And what's more important is that, of course, we would love to consider a system in some finite volume and only then send the size of the system to infinity. So because of that, these Q are solutions of what are called beta equations, and they put them in this way. And even though it's some nonlinear equation with some phases, some entanglement equations, all solutions, or in most cases, they are parameterized still like free fermions, namely just by just integer numbers that also obey Fermi principles, so they just cannot be well the same numbers. And it's very easy to represent these numbers as this red circle. So always when I will be speaking about a vacuum, so these numbers they will be just consecutive numbers from minus n to n. And if on top we have some excitations, there will be well some numbers that would correspond to excitations. All right. So now the task is, okay, so you imagine even you solve this guy, so you know the states, you know also matrix elements. Now the task is how to perform the summation. And again, the summation has to be performed out of, n particle ordered integers. So all possible combinations such that none of integers coincide. So how to do this? Well, of course, there are ways to develop to address this problem. And in case of low temperature, namely when these integers they correspond almost to the vacuum state, there are like powerful methods. So either you can do numerics on this, and it's quite easy because you can iterate the sum rule. So you can pick the most relevant momenta k. And that what goes by name of Abacus, for instance, or other algorithms. And here's like the most, I would say, canonic picture that Jean Sebastian always shows at his talk. So I always want to show. So this is a relation between experiment of, so I think it's some neutron scattering. So it's like a spin-spin correlation function just for E of it that I mentioned, and this result of experiment, and this result of beta ansatz. And then you see that it's like remarkable description. So this is one approach, just to do numerics, and another approach is to say that I'm interested in the most universal features of this correlation function that happens at large distances. And you see here, like the most weight is concentrated, well, very close to edge of spectra here. And then there are like very powerful field theory methods, namely Legendre field theory, that describes you edge behavior of your correlation functions. However, this is all works at zero temperature, but at finite temperature, both these approaches fail. So first approach failed because numerically it's very difficult to saturate the sum rule. So you have to take exponentially many terms to do this. And the field theory approach, well, since we focused on the edge of spectrum, we kind of linearize spectrum of excitation. And it turns out that if temperature is reasonable, it's no longer valid. So well, one of the motivation was well, how to deal with this system. So now, since problem like lies in these summations, we can use like the most simplest models that also have this type of summation and see what we can do. And as an example, it will not be our model, but just a motivation. So for instance, we consider again Lieb-Lininger model, but in the hardcore limit. And so here I choose so please don't confuse with raw introduced previously. Here I just consider a 2-point function, which is field. Again, it can be computed just introducing the resolution of unity. All these guys are known, and energies is just sum of k squared, moment is just sum of k, and all quasi-momenta, they're just solution of better equation. And now you see, then if we consider hardcore limit, namely c to infinity, then first of all, this classification that all states are parameterized by ordered set of integers, it survives. However, now these beta equations, they are very simple. Namely, this is, well, depending on the parity of n, it chooses such that when I send c to infinity, it will be -1 to the power n plus 1, such as just 1. So this q is just this, and the k, because it's different number, they just shifted by 1/2. So this is like very simple, and the result for this correlation function, it's expressed in this simple Fermionic determinant of the sign type. This is what is called by Linear formulas. This is like zero temperature result. And just to be like absolutely sure, when what I mean by Fermionic determinant with these kernels, it means that the operator acts on function by convolution with this kernel. Right? And it defined on some contour gamma. In previous example, it was contour from -kf to kf, but it's very well-defined object. And what is more important for me, that it object can be easily evaluated numerically. So there are like powerful techniques. So whenever we see Fermionic determinant, it's as good as just a definite integral. So and it can be computed similar techniques, namely by the quadratures. And yeah, okay. So now idea is to consider some kind of observables that are type of this Fermionic determinants, but they would correspond to finite temperatures, and then try to find the asymptotics. And since we have all control of numerics, then we'll try to develop some theory. More specifically, we will be interested in what I will call tau function. So it will be my sun kernel with some distribution function, which I call an f of historical reason, that well would correspond to finite temperature. So this will be like some probability distribution function, but not necessarily. And here I also introduce some parameter nu. So previously nu was just 1/2, so it was just a shift of fermions, but now it's just it's just a parameter. So this will be one of the example, and another example will be latest version of this, and it will be already physical, I would say, correlation function of Smith-Spin correlation function in X model. So the only difference here is that we have this sign instead of p minus q and some finite rank correction. Otherwise, it's the same structure. So, and observables like this, they appear in many places in theoretical physics and mathematical physics. So first of all, well, the most known example is probably emptiness formation probability in random matrices. My personal experience was with this object when I encountered some like mobile impurity, and so and not always these objects are related to free fermions. So for instance, this nice work of Jean-Marie Stéphane, who showed that this Loschmidt echo type of observable or return probability from the domain wall, it's also of this type where instead of NF, we have this function e to the minus p square. And there are other examples. So the most important probably this classical integral systems where the role of the NF is played by the reflection coefficient. So so now it would be nice to be able to evaluate large X and large time expression for these guys. And that's my talk will be about. Okay. So to do so, I'll first come back to the form factor presentation and show how this object can be can appear as two-point function. So I will not specify you what is the operator. I'll just specify you what are its matrix elements, and usually it's enough. So again, I will have my normal fermions and shifted fermions now with parameter nu, and for my operator, I'll just choose this matrix element, which is just some constant and Cauchy determinant, right? So it has some physical interpretation in terms of anyone, but right now it's not important for me. What is important is that because of this simple structure, this sum can be computed explicitly. Namely, we have product of two determinants, so determinant square. Then we can insert this summation inside of determinant and get determinant of one matrix. So it's some kind of variation of Cauchy-Binet formula. So that's what we'll have. Then we have to work a little bit careful with I equal j to extract this one. And then we'll have so some kernel which will be coefficients at 1 over L. And in the thermodynamic limit L to infinity, we'll just reproduce this expression. And now the question is, how does it help us to find the asymptotic as large X? Because the typical way to deal with this program, with this determinants, is to solve Riemann-Hilbert problem, to formulate it on the interval from minus kf to kf, and then use some approximation. So normally it's very complicated business. But here we'll use more physical approach. Namely, we just say that we'll find asymptotics of the Friedholm determinant not from this thermodynamic value, but rather from the form factor series. And the way it's done here, it's like this. So now it's very schematic. So still it's zero temperature, I remind you. So we'll find the most relevant vector here. It will be a vector with whose integers are almost the same as q, almost the same as q. Still, and we computed in large and limit for large system size, and it will decay, which is just a reflection of the orthogonality catastrophe. So yeah. So now to get finite answer, we have to just get some modes, and there will be this soft mode excitation around this vacuum. So we have to sum over K, and we replace like the full sum over only soft excitations around this vacuum, which is schematically shown here. So we'll not consider excitation of order of n particles, but rather order of 1 around the kernel, around the edges. And we cannot go really far because still we have this Pauli principle. And for these excitations, we can simplify actual matrix elements and identify them with matrix elements of the auxiliary free Gaussian field. And then this computation is very easy, and it just gives us this nice answer. So this is what in a nutshell is Bosonization. But contrary to normal Bosonization, where you just identify your operator with some operators in Gaussian field theory, here we also have prefactor. So normal Bosonization, normally you have just exponents. And and how does it work? It's just this n is replaced by these guys. So this is in a nutshell. And if you have like other excitations, for instance, if you have time and you have saddle point, for instance, when you consider dynamic operational functions, there could be also other contributions, which goes by name of nonlinear Latinger liquid, and they would correspond to normal summation of the position of the very hard excitation. So not only soft excitation, but one hard excitations, but its summation, well, it gives like normal saddle point, and in addition to this power law behavior, it just gives square root of t. So this is a story developed with this gentleman, and it corresponds to T0. So I would love to see how it generalizes. Right. It's a nutshell. Now let me show like simple example how it works for our signed kernel. So first of all, we have to evaluate this guy. So let's see how it's done. So we just choose K with the same integers as Q. We present Cauchy determinants as a double product. Then we have double product of integers. So first product of integers give us ratio of gamma functions. And the second product of gamma functions give us ratios of Barnes functions. So this is quite simple computation. And when we send n to infinity, we just we just arrive at this simple formula, right? And then if so here we consider it new constant, but if new would be some smooth function of k, nothing would change much. Just we will arrive at this expression. All right, and now the result of Bosnianization says that this n will be just replaced by x, and here it is. So this is asymptotic for tau function, and here it's comparison. So dots are exact computation for Golomb determinant, computed by some quadratures, etc. And red is just this simple formula. And you see that except of origin, where basically this diverges and this goes to 1, in all other points it's more or less perfect, right? And a similar story comes when we take into account time. So it's just small modifications plus this square root of t corrections that I told you. And again, a part of x equal t where it's not even like properly shown, or yeah, maybe here. Everywhere else, this asymptotics work just perfectly. All right, now this was a review of zero temperature techniques. Now let's see what will change if we introduce finite temperatures. So what if we introduce this NF here? Now our microscopic and now all the soft summation would not really work, because first of all we don't have edges. So we have a lot of soft modes, and more or less, if previously our overlaps they died with the power of system size, now they will die exponentially. So it's very difficult to do any bookkeeping in the previous way. So what we do instead, we use a heuristic approach. So we'll just notice that what if we would consider some fermions with a artificially constructed phase shift, which here I call nu t, such that this equality holds. Then this would correspond just to zero temperature, but where all the positions are filled, but with some effective phase shift. Then my technique would work again, and then I will arrive at the asymptotics immediately. So once again, it's kind of important point. Let me maybe write it down at Blackboard. So we would like to evaluate some Golomb determinant at finite density, yeah, or finite temperature. Then we say, okay, we replace, and it depends on some parameter nu, yeah. Then we replace instead with more or less same kernel, but with modified shift that now depends on rho, plus there will be some corrections, of course. But then for this guy, we know that this sum of form factors, whatever it was, exp. Now the sum, it consists basically of one term. Because why? Because here we took all possible integers from -infinity to infinity. So basically it's just one term. And of course we have to work a little bit to evaluate it the same as we did with this double product, but that's it. So then this is just some answer. So it turns out that this determinant is just some simple function, well, written here. And now then of course we have to say why we can approximate this, but let's see how it works. Right, and of course these effective form factors, they are not really physical. Even this phase shift is complex. Now some complex function that depends on the state. And because of this, we kind of, in fact, get correct answer, because now this new is complex, and now instead of power law behavior, we have exponential behavior, which you expect for the correlation function at finite temperature. So, and of course, there will be some coefficient. So, and here I just compare. So again, red is my asymptotics, and the blue dots are numerics from the front globe. And for small temperatures, well, you still see some oscillations, but yeah. And for large temperatures, it goes immediately into over-damped region. But again, difference between blue and red, yeah, it's almost yeah. It's so starting from x equal 5, it's already almost indistinguishable. Right, and for instance, another prediction, of course, that we can get is the correlation length, or the rate with which correlation function derives. And again, and here it's for any temperatures, yeah, the comparison is just identical. So dots again are just frequent determinant, and the red is just imaginary part of this formula, of this new. Yeah. Yes. For instance, you can view it as this, indeed. Indeed. I mean, I never introduced e to the minus beta h in traces, so all my temperature was like in the initial distribution of the skews. But probably you're right. Yes. Yeah. Right. Okay. Yeah. Thank you. Yes. Yeah. Okay. Because for this, right, for this observable, here you have the same number of k and q, right? The same number. Well, it's just by construction, I'm telling you. And now you took all possible integers from minus infinity to infinity. So basically, you don't have any excitations. So previously, why there was some here? Sorry. Yeah, why there was some here? Because these guys were filled and these were empty. So you could be able to put some excitations and create particle holes. Now imagine all these blacks are just filled. So there are no way to create any excitation. Right. So you see, that's the difference. You at the final temperature, when you're here, yes. But now here, all this gone, so this is as if you have zero temperature, but it's both advantage and drawback. Because now I capture correctly leading term, but with subleading, I will have some trouble. Yes, but very good. There will be one small exception of this rule. Right. Okay. So and the correlation length, just one last thing. So since we have exact expression, we can check when CFT prediction that says that inverse correlation length is linear with temperature. Well, it's yeah. So you see the temperatures of order of Fermi energy is still okay, but then it's not really linear function. Good. And now exactly to question of Jacopo, is there some modification of the scheme? And to get this modification, we consider a latest version of this model. So basically, it's just XY model. So there's just spins with anisotropy and magnetic field, and it can be diagonalized by Bogoliubov rotation. It has a spectrum that has gap and Bogoliubov angle. And I will use for my spin correlation function, I will use a result of this paper because it's immediately in terms of Fregom determinants, which is nice. So so it has this extra finite rank correction sign in denominator, and this effective distribution, it turns out to be complex. So this is just like new, otherwise it's similar story. And we can try to proceed to evaluate large X expression of this guy as we did. Except here we have to modify our matrix elements, or sorry, so it has to be O here, but okay. So first of all, here instead of like normal ratios, we have signs, which means that all momenta are defined from 0 to 2 pi. So it's just in Brillouin zone. Brillouin zone, it's called. Right, and yeah, but otherwise it's the same. And again, we kind of use this effective form factors, and again we express effective kernels up to exponentially small terms, and from which we now knew our well, effective phase shift and how it's related with parameters for the model, namely the spectrum and the Bogoliubov angle. But now we see that from this expression, actually, this guy, when k runs from the Brillouin zone, we might have some non-trivial winding number. So it depends on parameters, and in principle, this delta can be plus, minus 1, and 0. So in ferromagnetic regime, it's plus minus 1. In paramagnetic, it's just 0. And it happens, of course, due to this Bogoliubov angle. And now, yeah, and one more important, because of this finite rank, the number of k's is 1 bigger than number of q's, and that's kind of like small technical addition. But believe me, all this summation, all this Cauchy-Binet works just fine, and you produce like finite rank. Okay, now we can since all numbers must be in Brillouin zone. The total number of solution, it depends on this delta, and one can show that the total number of solution of this equation, the Brillouin zone, it's actually not L but L plus delta, and delta can be negative. Yeah, so well, the way to show it is just yeah. So here's like a simple proof. We just go from a nu that has non-trivial winding to nu that has trivial winding, which we call nu delta, and then equation just transforms like this, and then just the number of yeah. Yeah. So solutions is like this. So now remember the number of k 1 bigger than the number of q. So now if delta is 1, then again we in the same situation as we had before. So we have exactly one term in our sum. So we just had all possible k's and all possible q's. But now, but if, for instance, if delta is 0 or negative, then we have a problem. Even if we put maximal number of k in the yeah, sorry, here it's a little bit interchangeably. Now k is outer state and our q with sum. So now if we put, let's say delta 0, now let's say we fill in initial state all possible k, all possible solutions, then q should be one less. But there are LQs, so one we have to throw away. And which one? Well, basically, in this summation, we have to sum over all of them. So now instead of one term, we have this integral overall position of the whole, because it's just so this sum, instead of being just one term, it's now just sum over all possible solutions. So here it's well, yeah, shown schematically. So this should be one bigger than this. Right, but otherwise everything works as before. So and if delta is -1, then it's 2 integrals and etc. And here's the answer. So here is in formulas what we just said. So if delta is 1 minus n, then we'll have n holes, out of which we have to sum. Then we have to form this kind of determinant, which is n by n, and n is this well, this delta. Out of which well, but then under determinant, it's this simple expressions, which just contribution from one whole summation and some overall factor as usual. So usually we just didn't have sign here, but otherwise it's more or less the same. Well, okay, so this is a nice expression, and yeah. So basically now coming back to physical observables, so we have different regimes, delta 1, delta 0, paramagnetic. Then we have prediction for the correlation function, which I call tau function, but okay, which has some prefactor and correlation length. And here are like explicit expressions through the parameters of the system. So what's interesting is that in correlation length, it looks like as if it's the same integral plus you get some correction. And but in fact, so here we can compare again. Dots are just numerics, and blue is asymptotics. And to show you any like visible difference, we have to go to ridiculous anisotropies like 5 and a large temperature. Yeah, and here again, like dots are extraction from the correlation length and prefactor. You see, it works very nice. And here I showed this blue. It's just this integral. So if you just plot this guy, even though it looks like continuous function of parameters of the system, well, in fact, it's not. It has this type of cusp. But if you just add these corrections, then everything is fine. And that's how it should be, because yeah, right. Okay, very good. Right. So now a little bit bonus, since I have some time. How normally correlation functions in these systems were evaluated. So normally they were not evaluated through Fredholm determinants, but rather through Toeplitz determinants. So Toeplitz determinants is just when yeah, function matrix depends of n minus m. And first we have to establish this relation between our Fredholm with our assigned kernel in Toeplitz, and it's done by this formula. And the proof is more or less using this formula. So that AB is equal to that BA. So here's so small. And now from the asymptotics, we expect that since asymptotics, yeah, it depends only on nu delta, which is basically whatever is your nu, it brings you to nu with zero winding number. We can expect that at least asymptotically, correlation functions should be related with different nu. But it turns out that not even asymptotically, but for any nu, we have this nice relation. So here a nu is whatever it is, and nu1 is just shift by 1. Yeah, I don't know. So I never saw this formula, so we think it's nice. And of course, normal way to evaluate asymptotics of Toeplitz determinant is by Siegel formula and Hartwig-Fisher. And yeah, here we kind of identify what we had before and what I presented you. Yeah, and of course, this model was beaten to death in the 70s. And we can compare what we obtained with the answer. And here it's a result from Baruch McCoy, and yeah, that's how it presented in the paper. But now we have like one nice exponential of double integral, which is a little bit better. I must say it's also reasonable if you don't have powerful computers. So this product to evaluate numerically is much better. So probably in 71 it had some meaning, but now like double integral is much better. Right. So finally, let me tell you. So far everything was about finite temperature, but for static case. Now, how about dynamics? Because you remember at zero temperature dynamics, you had this funky one square root of t corrections that came from the hardcore excitations. So how about in this case? So we can consider, again, we can include time, do the same procedure, obtain kernel, and we'll try to find effective phase shift for our effective fermions. However, here it will be a problem because here it seems like inevitably we have to consider only asymptotic regime. Only this regime we can solve, and unfortunately we could not find a continuous solution for nu. And it does not seem to be like drawback. It's. I think there are no solutions like this because even if you look at the leading term in the exponential, you expect that in the asymptotics, final result should be some integral with absolute value of x minus tk. And this can be only if nu contains some kind of discontinuity, at least in imaginary part, such that you would never have a growing correlation function. So I think there is some discontinuity. We don't know how to regularize it. We presumed it regularized somehow. So otherwise it should be like a real jump. So sorry, this is for continuous. This is picture for lattice, but okay. Otherwise, it's fine. And now, why it's bad to have discontinuous nu? Well, in the main reason why you don't want to have discontinuous nu is very utilitarian, because in the formula for asymptotics you have this double integral. So it's x and then double integral nu q minus nu q prime q minus q prime squared dq prime. Now you see, if your nu is discontinuous at some point, then you integrate from q from minus infinity to this point, then q prime from this point to plus infinity. This is finite, this is 0, and you have some divergence. And what is this divergence? Well, square, it's some logarithmic divergence. So now if you argue that it's regularized by square root of t, well, then you have some prediction for your correlation function and some constant at which, unfortunately, you don't have control because it depends on your regularization. So previously we had prefactor, now we don't, but at least now we have this interesting power law behavior in the tau function, and I think it's quite universal. So it's nice to understand what it means and how it can be obtained from any summation, since all positions are taken. So it's absolutely mystery at the point. But there is this phase shift, and it depends on position of x and t, and it depends on state. So whatever you put here, yeah, this power seems to be like this. And for some models, yes, indeed there are predictions, but of course this is much more difficult to check numerically. For lattice anyons, which we checked it in this picture exactly from this paper, but so far there are no clear understanding like what's going on. All right, so with this I would like to conclude. So what I kind of told you today is a way to avoid solving Riemann-Hilbert problem to evaluate asymptotics of Riemann determinant, which resulted in basically dressing of the phase shift of fermions and making state dependence complex and whatever is necessary. Depending on the system, whether you're on lattice or not, there are different types of these contributions. In best case scenario, just one term, but always it happens. And I believe so these results are, well, quite universal. In particular, this last statement about this extra power law on top of exponential decay. I think it happens whenever you have a little point in the spectrum in your dispersion. And of course, it would be nice to relate with other approaches developed for addressing correlation function at finite temperatures, such as quantum transfer matrix, thermal four factor developed by Jacopo and Milos. And then we can also apply it to other systems. For me, the most interesting is like to find asymptotics for classical integrable systems like nonlinear Schrödinger, and that's okay. So with this, I would like to thank you for attention.
Thank you very much for your talk. Does anybody have a question?
Okay, so why work now in the real space? Do you think it would be simpler to work in momentum space?
But it was all in the momentum, no? So yes. Good question. So the question was because all experiments and all interesting stuff they done for Fourier transformation of the correlation function. Now Yeah. Yeah, I don't know how to use these methods for momentum, and it's not clear. Yeah. I mean, yeah, but it's a good idea, because then instead of exponential, you have delta functions inside, and then yes. No, it's a good idea, but how to? What's good about exponentials that they factorize, and then you have this freedom determinant. With delta functions, not so much.
When you treated the ground state, you took into account excitations close to the, let's say, Fermi point, and also higher lying excitations, impurity band.
Yeah.
Why didn't you take into account a whole impurity band?
So there are, so either you can go deep into the sea to the edge, and then your impurity will be whole, moving, or like what I showed, you go from the edge of Fermi Sea somewhere outside. It depends on your momentum you want to allocate.
But you need to take okay, so that you never have to take into account both.
You can have to take both. You have to take more excitations like this, but there will be higher powers. You have to take into account both. Yeah, it just was.
Thanks.
Further questions?
Yeah, so you had a correspondence between Toeplitz determinant and Fredholm determinants.
Yeah.
And it's more complicated when there are Fisher-Hartwig singularities on the Toeplitz.
Yes.
And so what kind of singularities would this correspond to?
So Fisher-Hartwig corresponds to what I told you about zero temperature. So when you have distribution that suddenly stops.
Okay.
And then in my opinion, it's easy. So this was more complicated. But yeah, in Hartwig-Fisher, you would, if you map, but by the way, this map works only for zero time. For static correlation function, for even, but okay, yeah. So you would have not the full circle, but rather you have a symbol that is disconnected. So it will be on some arc, one value, then its other value. And,
okay. Yeah.
But I believe it maps to the zero temperature case where there's power loss, but it's not that clear. I mean, yeah. So this is like a bonus. This is not the main approach.
Does someone have another question, maybe? All right, if not, let's thank the speaker again. And